This is level 2 of the CFA program, Quantitative Methods, and the reading on multiple regression, which is a logical extension of the previous reading, Simple Linear Regression. All we're doing is adding some independent variables, and there is going to be some benefits to this. Of course, we're going to have more explanatory power, but there are some costs associated with adding more variables. Now, the good news for you is that these learning outcome statements are virtually identical to what we just did in simple linear regression. However, remember I just said that there are some costs associated with adding some variables, and that's what we do there in those last 4 or 5 learning outcome statements. So let's get right to it. You should remember from simple linear regression that we're trying to use an independent variable to explain a dependent variable. And of course, multiple regression analysis just leads us to lots of independent variables. So look, we have those words independent variable in purple. So we have an x1 and an x2, and we could have an x3, an x4, an x10, an x20, all the way out to xk. Y is still our dependent variable. We're still going to have an intercept term. We're going to have slope coefficients. But now, instead of just calling it the regular old slope coefficient, here in multiple regression analysis, we're going to call those partial regression coefficients. And then there's the disturbance or the error term all the way out at the end. Now, once we collect some data and then estimate a set of linear parameters, we get that equation, the estimated regression equation that's in the dark blue box. Notice that there are little hats on top of some of those outputs, and that just means that it's estimated. And so what we're trying to do here today in multiple regression analysis is exactly what we did in that previous recording. Remember, there was that slide and there was a graph with a bunch of orange points, and we were drawing a line. We were trying to draw a line in between those points to minimize. I even did this on that last recording to try to minimize that distance. Well, we're doing the same thing here. And there's that residual equation that we had before, each of the individual y outcomes, y sub I minus their estimated value. But now we're doing it in multiple dimensions, right? Multiple regression analysis. So we still have the y-axis as the vertical axis, but now instead of having just one x on the horizontal axis, we have an x1 and we have an x2, and we could also have an x3 and an x4, and you could have as many x's there. So it's kind of 3 dimensions. And so that's why it should be obvious here why we're looking at partial slopes, because, you look at the blue box, so, at least visually, you can see that the slope is just a little bit different for x1 and for x2. Now, how are we going to interpret these estimated regression coefficients? Now, these are called partial slope coefficients. And so each slope coefficient is the estimated change. Remember, I said this to you in the previous recording, that think of it as, kind of measure of sensitivity. So when you have a 1-unit change in the independent variable, then you're going to have that corresponding change in the dependent variable. And so it measures sensitivity. How about if we look at this model here? Y is equal to 0.6 plus 0.85 x1 plus 0.65 x2. The first thing that you should observe when you look at that purple box is that there is a plus sign before each of those partial slope coefficients, indicating a positive relationship. So as x1 increases, then y will increase, and same thing with x2. But how do we specifically interpret this above equation so we can handle that LOS? So a 1-unit increase in x1 will result in a 0.85 increase in y. And then notice what we have written there, keeping x2 constant. So that's an important part of that interpretation. And then of course we do the same thing with x2. And then what about the intercept? That really is the answer to the question, well, what if some strange reason x1 and x2 are 0, then the value of y takes on 0.6. Now, how about the p-values with those associated partial regression coefficients? What we're trying to do here, and there's a good picture of the bell-shaped curve, and of course this is going to be a two-tailed test, and I'll show you that specifically here in just a few moments. But what the p-value does is the smallest significance level at which we can reject some null hypothesis. And the old-time gods of econometrics came, and when I say old-time, I'm going back, hundreds of years. These individuals came up with the idea that 95% ought to be a big enough chunk in the middle so that you can statistically test. Now, of course, as we've evolved over time, we've realized that 95%, it might be good for some data sets, but it might not be good for other data sets. How about if I cue our future discussion on value at risk and exposure for that? But I'll go ahead and explain in more detail that p-value when we get to an example and a table. All right, let's go ahead and formulate a null and alternative hypothesis and then do a bunch of other stuff. Boy, look at this LOS. I remember when I was a candidate, I never liked LOSs that had a whole bunch of commas in there, because then you have a whole series of LOSs that are probably related. And so this is a big one. It's a long one, bunch of commas in there, but it's okay. Let's not be too intimidated by it. So skip down to the bottom there in the purple. This is our null hypothesis. So this is how you do this. You say to yourself, okay, what if I'm totally wrong? That's my null hypothesis. So I design the test I want to reject the null hypothesis. So I say that partial slope coefficient is equal to 0. I set it up so that if I'm right in developing my model, then I'm going to be able to reject the null hypothesis. Versus the alternative hypothesis, where the slope coefficient or the partial slope coefficient is not equal to 0. So there's your key there. The not equal to 0 means that it could be on this side of 0, and it could be on this side of 0, which means that it is a two-tailed test. Now, once we go ahead and estimate this set of linear parameters, we're going to have to test whether or not those partial slope coefficients are different from 0. And so look up at the middle there, there's the test statistic, and this is exactly like it was back in the simple linear regression model. So we have the estimated regression coefficient. We're going to subtract out the hypothesized value, which in many, many cases is going to be 0. But I think I said this to you in that previous recording that, if you're testing that the beta, you could test the beta of an individual stock or portfolio of stocks is significantly different from one. Maybe you want to ask yourself, does my portfolio look like the S&P 500 index? So you could do it that way. And then we divide by, of course, some kind of a standard deviation. We always have to divide by a standard deviation. Here we call it the standard error of the regression coefficient. And then because we have multiple independent variables, our degrees of freedom has to change. So we're still going to do the n-1, but now we have to add all of the extra independent variables so that we have a test statistic now that has n minus k minus 1 degrees of freedom. All right, let's take a look at an example here. We have an economist testing the hypothesis that interest rates and inflation can explain GDP growth rate. 73 observations. So this economist comes up with the following regression output. And so I'm guessing that you would be prepared in any kind of a question like this, not just quantitative methods, but economics and other areas, to get a table, a regression output table. Here's the simplest of all possibilities. So we have the regression independent variables going down the left-hand column, their coefficients, and then their standard errors. So look at the bottom teardrop point. Test the significance that the independent variable interest rates at the 5% level. So we're just focusing on the partial coefficient of interest rates, which is the 0.25 and the 6% standard error. All right, so there's our There's our null hypothesis that the interest rate beta is equal to 0 versus does not equal to 0. And so what were those observations there? We've reprinted those. So 73 minus 2, we have two independent variables, right? Minus 1, so that's 70 degrees of freedom. And so you can get out your old t-tables and run your finger down and run your finger across, and you'll get somewhere around 2. Remember, I told you this back in that first recording, that my econometrics professor said, you know what, when we're doing stuff, and we always do, stock returns and market returns and bond returns and index returns, and so he always made us collect, thousands of data points. So 2, that's a general notion. But of course, on the exam, you need to make certain that you go run your finger across and get that precise critical value for t. So there's the test statistic. That's a super simple math. So 25 minus 0 divided by the 06. So there's 4.1. So we know, we didn't even have to look that up in the table. 4.1, that's probably going to be, especially with 73 observations, that's going to be, we're going to reject the null hypothesis. You can see over there in our illustration, there's the 1.94 critical value. And then, of course, you have to go all the way over to the other side of 0. There's 1.994 is the other critical value. So we're interested in the tails, and that 4.196 falls in the tail, one of the two tails, right? So, let me go back here. So the fact that the coefficient of interest rates was 0.25, that was positive, and inflation 0.2 was positive, means that we're going to be looking on that right-hand tail. If in fact they were negative, then we would be looking on the left-hand tail. All right, let's go ahead and interpret the results of a different regression model. And so what are we doing here? We believe that the returns on growth stocks and the returns on value stocks can explain the return on technology stocks. Observations is 60, so there's the output. And to get the test statistic, all we really need to do is take one column and divide it by the other column, assuming the null hypothesis is that the partial coefficient is 0. And so we get the test statistics over there on the right. So we have 0.4, there's no way that's significant. And then we get minus 0.9, there's no way that's significant for value, but then the growth stocks, we get 5.9. All right, so how do we interpret that? There's the critical value, 2.002. There it is. Once again, it's around 2. And so what are we saying here? In summary, that the test statistic for growth stocks, which is nearly 6, is going to be statistically different from 0. The test statistic for value, which is 0.9, that's not going to be. So we reject the growth stock null hypothesis, but we fail to reject the value stock hypothesis. And so we make some kind of a conclusion saying that, hey, you know what? Growth stocks are doing a much better job of explaining technology stocks than value stocks, which, we can knock on our sides of the heads and say, hello, McFly. That seems like an obvious notion here. Here's another LOS that we did back in that simple linear regression. Let's go ahead. Let's look at some confidence intervals, and then let's look at a predicted value. So the equation for the confidence interval is exactly like it was before. Let's go ahead and take a look at an example. Swinging back to our example on interest rates and inflation rates, let's go ahead and look at the results. So just a summary here. So we're going to say, what was our partial slope coefficient was 0.25. So that's going to be, our estimated value. That's kind of right in the middle. And then we're going to do plus or minus. So we want to go this way and we want to go that way. So we go back and get that critical value, 1994 times the standard error of 6%. And so you put that in your calculator. And as far as I know, there's no way to do this in this calculator. Maybe there is. I can't find a plus minus button. So you got to do the plus first, get an answer, and then do the minus and get an answer. I always thought this was fascinating when my econometrics professor would say this. So we would do, let me go back here. We would do this confidence interval, And 0 is not contained in that. Remember, we're doing 5%. So 0 is not contained, which means that the regression coefficient is statistically significant at the 5% level, which was the same conclusion that we made earlier with that t-stat. How about the second part of this LOS? To look at the predicted value of the dependent variable. So look at the bottom. So we're just repeating a lot of stuff on this slide, but look at the bottom left. Assuming that interest rates 12% and inflation is 6%, estimate the predicted growth rate. So all we're doing is getting our y-hat model out, right? So we're predicting GDP, and then we're just going to substitute all of those coefficients. You know, there's the 04, there's the 25, there's the 20, and then multiply them by the question stem. So in the bottom left, the CFA Institute would have to give you the values for X1 and X2, which they do, of course, 12% and 6%. Notice up at the top, that second line, can explain GDP growth in a country, not your country or not the United States where I live, just a country. But remember, the CFA Institute on the exam, you know, they're not trying to mimic a particular country's current level of interest rates or inflation or GDP growth. Now, however, having said that, of course, they'll probably not give you an example where you would get a predicted GDP growth rate of, 500% or some crazy number. How about the assumptions of the multiple regression model? I want you to skip down to the final 4 of those, because these are the differences between the first 3, which are identical to the simple linear regression model, right? It talks about dependent and independent variables, randomness, no definite linear relationship. But remember I said to you earlier, there is a cost associated with adding extra variables. All right, so we're going to say variance is equal. That was the same thing, right? The error term is uncorrelated, right? Error term is normally distributed. Well, we had some possible violations when we did the simple linear regression model, but now we've got tons and tons of potential violations there. So that's probably the focus of this set of questions, on what happens if those assumptions are violated. We'll, of course, look at that at the end of the slide deck. The next LOS really could be called something like, hey, do you remember we wasted your time back in simple linear regression doing the F-test because F and T gave us pretty much the same result? Well, now the reason that we didn't, and the reason that it wasn't a waste of time, is because we wanted to expose you to the F-test back in simple linear regression, so you got the basics, so then you would really super understand it once we got to multiple regression. All right, so the F-test is the null hypothesis is that the slope coefficient 1 and the slope coefficient 2 and the partial slope coefficient 3 and 4 and 5 and 10 and 20 and 100, that they're all equal and they are all equal to 0. This is versus the alternative hypothesis that at least 1. All right, so don't fall into that trap on the exam that it's all of them, that all of the slope coefficients are not equal to 1. It's just at least 1. And the F-stat equation is given right there. We did that back in simple linear regression. And what you'll see in a table is that what you're probably going to do is use the table to use this formula, and it'll be really super easy as when we start dividing things. And I'll show you that here. I'll show you that here in just a second. Let me make one comment here that probably won't show up on the exam, but as a good academic, I feel compelled to let you in on this. I'm pretty sure the F-statistic was originally crafted to test for differences in variances, and so you do a ratio. So variance, of course, is squared, and that's why the F distribution starts at 0, because it's a squared number. And this is going to be a one-tailed test, and this is super important. It's a one-tailed test because what we're essentially trying to do is ask the question, do all of the independent variables, do they explain what's going on the left-hand side of the equal sign with that dependent variable? And One of the ways that we do this is by computing an R squared. Remember, we want to have a high R squared so that we have a really good model. Well, think about what would happen if there were a low R squared. Well, if this were a two-tailed test and you had a low R squared, then you might reject the null, which would be a total waste of time. You would say, look, my model stinks. It has a low R squared, but I'm going to reject the null because it's a two-tailed test. So it's just a one-tailed test. So you may want to just erase from memory the last 1 minute of your life. But I think that's important in kind of understanding the big picture. There's the graph of the F distribution. Notice that it starts at 0. Notice there is skewness in it. So that critical region out there on the right is going to be what we're looking for, one-tailed test. All right, here's this table. We've seen tables like this before, right, in this recording and in the previous one. But let's suppose here's the output of regression analysis. So we've got 65 observations. So we have some degrees of freedom. There are the SS's over on the far right. So test the null hypothesis, 5%, that all two of the independent variables are equal to 0. So here's our F test. So let's go ahead and first find the critical values. So we have a numerator and a denominator in the degrees of freedom. So we have two independent variables. So there's the numerator. So we've got the column 2, and then we're going to go all the way down. Now, what was that there? It was 65, right? So we had 65 minus 2 is 63. Now in this table, we don't go to 63. We round, and this is pretty standard. I'm guessing you know that from your stats days or any tables that you have consulted. Really doesn't make any sense to have a table with 61 and 62 and 63 because they're all pretty much the same number. All right, so we're getting approximately, notice we put approximately there, 3.15. So I'm guessing the Institute might use that word in there as well. Or maybe they'll give you the actual critical values for 61, 62, 63, 64, and 65, and then you have to pick from among those. All right, let's go back to the actual calculation. So notice what we're doing. The F is really just the relationship between, and here's this thing. So we're going to do 94 divided by 2, 67 divided by 63, 68 divided by 65. And so that gives us the MSR and the MSE. And so there's the F all the way out on the right-hand column. So that gets us 439, and there's no way that that's going to be significant. So we fail to reject the null hypothesis. So imagine this. Suppose this model were so bad that F were 0.002, and if this were a two-tailed test, that critical value might be 0.5 or something. So we would actually reject it. So there we go. That's important. One tail. Now, of course, this leads us right back into what we said before, but this is before in the simple linear regression recording. Now we're doing this in the multiple regression recording. So the F leads right into, and in fact flows from and flows into this coefficient of determination. So R squared. Now remember R is correlation coefficient. R squared is correlation coefficient times correlation coefficient, but now we have to call this the multiple R because we have a bunch of independent variables. But the equation down at the bottom is exactly the same as what we talked about back in simple linear regression. It's total variation minus unexplained variation over total variation. So I love that from a big picture standpoint, but of course you'll probably use the RS and the TS's to calculate it if you have to on an exam. But notice the LOS says distinguish. How about some drawbacks of the multiple R squared? This is one of the first things that I remember from my econometrics professors, both on the finance side and the economics side. I know that you don't care about this stuff, but I have a minor in economics. So I had a bunch of courses from economics professors and a bunch of courses from finance professors, and you get a different perspective of quantitative methods from both of these groups of individuals. But here's what both of these people said to us. Both of these sets of professors said, look, you can increase the R squared by just adding independent variables. Sometimes even if they don't make any sense. So you can get R square, and you can get it to go 70%, 80%, 90%. And as soon as you hit some magic number, you can say, oh, I have a great model. And you may, and in fact, you were probably likely to have added some independent variables that were pretty much worthless. So how do we fix that? How we fix it is that we adjust it. And so that's why the adjusted R square is super, super important. Notice that bottom teardrop point. It decreases when the added variables do not improve the model. So what we're saying is that from a purely statistical standpoint, we're saying that that extra variable stinks. Now, we may think this from a fundamental or a purely economic standpoint. We may say, hey, let's add the return on, the Canadian dollar versus the US dollar to our model. That might sound like a good economic foundation to add it to the model, but remember here, this is math, right? Quantitative analysis is math, and the math is saying, well, you may have a good reason from an economic standpoint, but statistically, that variable stinks. There's the equation for the difference between the R square and the adjusted R square. Boy, you'll have to decide whether or not you should memorize that. This is what I did, and I think I've shared this with you before. I had a whole page of formulas that I was going to memorize. And so a week before the exam, I would get these out, and I'd look at them, and I'd close my eyes, and I would say, okay, I got that one, I got that one. All right, so look at this. Illustrates what I was saying earlier about my econometrics professor. So we go from 1 down to 2 and 3 and 4 and 5, number of independent variables in the model on the left-hand column. And notice that R square increases, 75, 89. So we're increasing, but notice the adjusted R square, it increases, telling us that, hey, that second addition, that second independent variable, boy, that added a lot, right? Adjusted R square went from 74 to 88. And then adding the third one, we get a little bit, but then we start decreasing. And so that's the cool thing about adjusted R square. And my professors used to say, you know what, you need to look at both of these, but put like 25% weight into the R square. And then we'll worry about that when we hit multicollinearity here in a minute, but always focus on the adjusted R square. And here's pretty much a summary of what I've just been saying. All right, how about an LOS to evaluate? Oh, this sounds like you're going to get, a model, right? And they'll say something like, all right, here it is. In this case, we're back to our technology and growth and value stock. So here's a model with 2 independent variables, and here's the output. So there are the coefficients, there are the standard errors, and so the null hypothesis is that those coefficients are equal to 0. So all we need to do is take the second and third columns, put those in a ratio. We get the test statistic over there, and then the p-values over on the right. So the p-value for the growth stock return is less than 5%. So therefore, both the test statistic of 592, right? We already tested that. We know growth stock returns are significantly different from 0, but the p-value then confirms it. And this slide is just a summary of there. So implies that the growth stock returns significantly influence technology stock returns. And, notice that we put the p-value in purple up there. Of course, the Institute's not going to color code the regression output. So you might see, 0.0231 or some number that's less than 5. So remember, in the p-value column, you're looking for that less than 5. In the test statistic column, you're looking for something that's, about greater than 2. Those are probably good things to look for. And remember that the Institute is likely to give you, some of these outputs in the regression table and maybe ask you to calculate some of the other ones. All right, so there we go, critical value. Oh my gosh, look, it's exactly 2 in this case. All right, so there's a summary of what I just said from that previous slide. Let's look at an analysis of variance table. All right, so now this is a little different from what we have here. Let me just swing back here. So here's a possible output where we have coefficients and standard errors and t-stats. Now, how about if we're given just, now what's that ANOVA table? The analysis of variance in there. So we have a bunch of those, sum of the squares, right? We need the total, we need the mean, we need the error. All right, so here's an output where we've got 59 observations and 2 independent variables. So look, there's the SS for the regression, there's the SS for the error, and then there's the mean. So all we need to do is take, boy, what are we doing? This is what I was saying about dividing the columns. So all we need to do is take 0.16 divided by 2, that gets us the 0.08, and then the 04 divided by the 57, that gets us the, oh, there's James Bond rearing his head, 0007, not 007. And then the F is just the 08 divided by the 3 zeros and a 7. And so there's that 118, and there's the p-value for the significance of the entire equation. So what do we say? Yes, we like this because p-value is less than 0.05. Now, of course, what we can do, let me go back here. So there's our F as 118, right? So we can go back and say, let's get out our table, make sure we run our fingers across, right? So look, we've got 2 degrees of freedom in the numerator and 57 degrees of freedom in the denominator. So if we want to run our finger over and run our finger down, we get, well, there's that same number again, right? 3.15. So we say 118. Let me just go back and make sure you get this. So there's the 118, and that's greater than the critical value. And so, you know, we're going to say something like, hey, at least one of the independent variables significantly contributes to the explanation of that dependent variable. So we can do this. Let me go back to this table. We do this 2 ways, but they're both going to give us the same result. The F, compare that to the critical value, and then P. All right, what we've been dealing with up to this point is a model in which we have independent variables like inflation rate and interest rate. And what did I say? The return on the Canadian dollar versus the US dollar. And we could add a bunch of those. So if you think about collecting data, you can actually go out and collect inflation data and interest rate data and exchange rate data. You can get all that data, and then you can get out your Excel and hit the regression button, and you'll have the outputs that have been shown you in this slide deck. But let's suppose that you have an independent variable that doesn't fall naturally inside of actual mathematical numbers. I mean, suppose that you want to say something like, hey, I want to estimate and determine and predict and explain the returns on some mutual fund, let's say, and I want to see if dividends play a role. Now, you could go out and collect dividend yields for all those stocks inside of the mutual fund, but then I bet a bunch of those stocks don't pay a dividend. So think about it. You have, as an independent variable, you have, you know, dividend yields of 4% and 3% and 2% and 6% and 2% and all those. But then for the non-dividend paying firms, you have a 0 dividend yield. And so suppose that you have 100 stocks in this mutual fund and 80 of them don't pay a dividend. So you would have 20 independent variables like 2% and 3%, like I said, and then 80 that are 0. And you have to scratch your head and say, well, there's no way that that's going to work. And that's why econometricians came up with this idea of a dummy variable. So you can say, hey, the dummy is equal to 1 if the stock pays a dividend, and it's equal to 0 if it doesn't. And this should make perfect sense. So notice that we call these a dummy variable because it's not really an attack on the intelligence of the dividend paying firms. It's just, hey, you either going to be a 0 or a 1. So notice that first arrow point. Quantify the effect of qualitative independent variables. So there's the binary variable, 1 or 0. Excuse me. All right, so let's go ahead and think of an example other than my dividend example. And a common test for dummies is to say something like, all right, we have this mutual fund return. Let's see if that return is identical for every month of the year. Now we're getting somewhere. So now we're not going to look at the actual. We want to say, okay, if it's January, it's a 1. And it's a 0 for every other month. And then if it's February, it's a 1 and a 0 for every other month. And so there's the complete dummy variable regression model. So there's the returns on the fund, right, or the monthly stock returns, whatever it is on the left-hand side of the equal sign. There's the intercept term. That's going to be important here just a second. And then we have beta 1 and beta 2, right, and beta 3. So we have January and February all the way up to November. Now, there are a couple of different ways to do this. And the standard inside of the CFA Institute model is to include an intercept term and exclude the December return, because that intercept term will then capture the last one out there. So you could do it by saying there is no intercept, and then you would have a B12 and December, but the convention, and this is the way I learned it, is just to let the intercept term account for that December model. So there's a summary of what I'm saying here. 11 dummy variables, 1 if the month is January, and 0 for remaining. And so what this is, do you remember, I'm not sure if we learned this back in level 1. Surely you learned this in level 3, that somewhere in the 1980s, there were a couple of professors who came up with this notion that January returns outperform every other month. And so this is how, or at least one of the ways that it was done back in the 1980s. To get that January effect. And so this academic paper came out saying, oh my gosh, January returns, they're this big. Every other month returns are this big. And then, of course, over time, we kind of figured out that maybe January returns are not this big. Maybe they're only this big. They may or may not be significantly different from 0, depending on things like, tax incentives and selling at the end of December and buying at the beginning of January, and wash sales and all that other crazy stuff. So notice the third circle point. The intercept measures the average returns for December, which is the omitted class. So the slope coefficient of each dummy variable estimates the difference in average returns between that particular month and that December month. And that should make sense. So here we have a regression output. So there's our model. Notice that what did we collect? London Stock Exchange data, monthly data, January 2006 all the way out to December of 2000 through December of 2018. So there's a total 155. There's the degrees of freedom 11 for the model. So the difference there for the residual. So there's the output. What do we have? We have the F of 241, and we have the p-value out there of 0.008. So we have, what can we say? So here's our null hypothesis. Slope coefficients are 0. Critical value is, what do we get there? So we have 11 degrees of freedom in the numerator, 144 degrees of freedom in the denominator. This is a one-tailed test, so that's 1.86 critical value. And so what do we say? So our F was 2.41. Was that number back there? Yeah, there we go, 2.41. So we reject the null hypothesis. So we say, hey, at least one of the independent variables significantly contributes. And then the p-value, right, what did we know that was? A bunch of zeros and an 8. So surely that's less than 5%. So significant results. So what do we say? We reject the null hypothesis that the returns are equal across months. All right, remember what I was saying to you in that first slide, or that first series of slides, that when we add these extra independent variables, we get more explanatory power, right? And so we needed to be careful. Let's not just worry about increasing R squared. Let's worry about increasing adjusted R squared. So let's live with all that stuff. But there are costs associated with adding extra variables. So one of the assumptions is that the variance of the disturbance or the error terms is constant across all observations. So look at the left graph. There's the line. There's our model. So the line, the blue line, is upward sloping, and notice that those disturbance or the error terms, they're, if you look at them, where are they? They're all about, above the line and below the line. So that looks like a variance that is pretty much constant. You can just observe that. Now, this is known as homoskedastic error terms. This is what we want. We want our model to reveal homoskedasticity. But then suppose that those the variances from the error terms don't look like that nice little coagulated straight line with the dots around them. Now they're spread out. Well, clearly, if you go to the bottom left of the blue line, there's some kind of variance there. If you go to the top right of the blue line, there's a gigantic variance there. This is called heteroskedasticity, when you violate that constant variance of the error term assumption. Now, heteroskedasticity, you might be thinking, is going to be a substantial problem, and it probably is. However, we need to differentiate between unconditional heteroskedasticity, in which the values of the independent variable are not correlated. They're not related to those error terms, the variance and those error terms. They're uncorrelated. So notice we have this occurs randomly, and this does not cause major problems. There might be slight problems, but it doesn't cause a major problem. The issue is when you have conditional heteroskedasticity, and this is when the variance of the error terms are going to substantially impact the independent variables. And so notice what we have in that red arrow point: cannot use regression for statistical inference. And so what happens then is that lots of packages will come up and say, flashing red lights, you have conditional heteroskedasticity, and we can correct it using some of this stuff. I have a slide at the end of the deck to show you how to correct for conditional heteroskedasticity. Now, sometimes, remember, these are independent variables. Sometimes the series of independent variables is related. This is called serial correlation. Now, this is much more prevalent in a time series, which is not what we're doing here. We'll do that in the next reading, and that'll be loads and loads of fun. We're going to call it autocorrelation. But notice the two pictures here, positive correlation. So what you have is that when you see something going, the next observation, you can predict that it's going to be in the same direction. So this is positive serial correlation. And then the opposite is negative serial correlation. Now, here's a good slide to memorize here. So incorrect computation of standard errors because of serial correlation, and it's going to lead to wrong conclusions and wrong inferences. And so this is what I would do. Notice we've got the orange and the light blue arrow points. I would remember these. Positive serial correlation, the standard errors are underestimated, t-stats are inflated, type 1. For negative serial correlation, just the opposite. Standard errors are overestimated, the F-stats the F-statistic is understated, and then it's a type 2 error. I would memorize those. How about multicollinearity? Remember, that assumption was that all of our independent variables are independent, right? Independent means that they're not related or they're not correlated. But suppose they are. Then you have multicollinearity, makes the slope coefficients unreliable, it inflates the standard errors, type 2 error, and so you really can't rely on those results. And here's the example that I have used in some of my classes if I ever get to this. Suppose that you're trying to determine how hot it is in your second floor bedroom, right? And one of the ways that you do this, you take an independent variable of the temperature outside of the front of your house, and then you have another independent variable, the temperature outside in the back of your house. So you have these two thermometers outside, you know, and all they're separated by is your house. So they're going to probably be highly correlated to each other. So you're going to have multicollinearity, which results in probably a much higher R squared. A high value of R squared, and a significant F test contradicts the T test. So this is how you detect multicollinearity. I mean, clearly in my example, that was an obvious notion, right? Temperature out front, temperature out back. But some multicollinearity results from less than obvious notions. You know, going back to my original example, you know, we have a measure of as an independent variable of inflation, and then what did I add? The return on the Canadian dollar versus the US dollar. Well, those may seem, at least on the surface, that they might not be related. They might be independent, but it might just be that there's a tremendous inflation component on the return of the Canadian dollar versus the US dollar. Slip over to your economics hat and say, yes, Jim, I do remember things like purchasing power parity and interest rate parity. So yeah, but here we go. Maybe they don't. So you actually go ahead and run the regression analysis and see if statistically that's a problem. How do you correct it? Stepwise regression to systematically eliminate variables until multicollinearity is minimized. You know, there are probably some really good ways of doing it. I remember my doctoral student friends and we would just say, okay, let's get rid of this one, see what happens. Let's get rid of that one, see what happens. Let's add this one and see what happens. And you end up, it's really not a good model. You end up just kind of playing a game of, you know, this is why our econometrics professor said, look, think of a model and think of it today and tomorrow, think of it for a month. Make sure your model is good, and then you won't have any problems with multicollinearity. How about model misspecification? This is the econometrics way of saying your model really just stinks. Selecting independent variables and the functional form of those independent variables. So model misspecification means you're just using the incorrect models, the incorrect variables. Either they're incorrect or the form that they're using that is incorrect. So that's what I have in what we have in that first one. Regression formula is incorrect. You can omit important variables. You can include irrelevant variables. You can have the wrong form of a data. You know, remember, you can hit your ln button on your calculator and transform data. You can hit your e raised to the x and transform data. You can multiply by 8. I mean, there are tons and tons of ways that you can transform data that will lead to misspecification. How about misspecified time series? This is going to be a super important conversation for us in the future reading. So notice the definition there. When independent variables are correlated with residuals in the time series model. We'll spend an entire 15 or 20 minutes in a future recording talking about this. But essentially what happens is that it's analogous to forecasting the past. And that's why we put those back to the future pictures there. Remember earlier I said, hello, McFly. Hello, McFly. There's George McFly. And there's Marty and Doc. One of my all-time favorite movies. I'm a big time travel movie fan, especially Back to the Future and The Terminator. All right, misspecification, biased and inconsistent coefficients, unreliable, inaccurate. I mean, what does that sound like? It sounds like when our econometrics professor would look at us and say, start over. How about a larger, bigger picture question in which we piggyback on our dummy variable conversation, but now we say something like, let's suppose that we want to have a qualitative model. So there are two kinds here. There is a probit model, and this probit model is based on all of the stuff that we did earlier on normal distributions. And what it does, this probit model estimates the probability that the dependent variable y is equal to 1 given the value of x. So probit, it's some kind of a probability model based on a normal distribution. The logit model is identical, but it's based on the logistic distribution. And then the discriminative model, the discriminant model, which is a form of the logistic model, it makes different assumptions. This analysis yields a linear function which generates kind of an overall score. And one of my colleagues in graduate school wrote his dissertation on bankruptcy. And I think he used, if I remember correctly, I think he used both a probit model and a logit model, but one of them was good and the other one was not. So look at the examples. There's that exact one, bankruptcy. So we can make a determination whether a company is going to declare bankruptcy or not declare bankruptcy. So let's go ahead and ask ourselves a summary question of what we've been doing all along here. Evaluate and interpret a multiple regression model and its results. All right, so let's go back to our technology and stock returns. So there's our model at the bottom there, y hat, 18146 and 1833. So these are our independent variables are monthly returns on the growth and the value, and then the dependent variable is the monthly returns to technology stock. All right, so how do we interpret this? The technology stock monthly return is 0.18. Here, let me go back here really quick. So if in fact growth stocks and value stocks have 0 returns, then the technology stocks will still have a positive return. So there's the 0.18%. All right, so a 1 unit increase in the growth stock increases the technology stock by approximately 1.5. So let's go back here. So there's the 1.46. So we make the 1.45, kind of rounding there. And then similarly, a 1 unit increase in the value stock decreases the technology stock by, whoops, I went the wrong way, by 2, because there's the decrease, right? There's the minus sign. So we need to make sure that we're sensitive to plus signs and minus signs in front of the partial regression coefficient. All right, here's a good couple of slides here. Steps for analyzing regression models. All right, so we're going to have a couple of these steps here. Examine the individual coefficients. All right, so check whether the model is correctly specified, and then perform a t-test to determine whether those individual coefficients are statistically significant. That's kind of like the first step. So think about what this is going to look like on the exam. Now remember, you're getting a vignette, so it's going to be, let's say a page or a half a page, then you're going to have 4 or 6 questions. So somewhere up on that question stem inside of the vignette, there's going to be a regression output and then a model, and they're going to say something like, okay, tell me about this. So that's where you perform the t-test and make sure, if you have 3 or 4 independent variables, make sure you test for the one that is being asked. All right, then ask yourself the question, all right, what about the overall? So we tested the individual slope coefficients, those partial coefficients. What about the overall validity of the model? This is where we look at the R-squared and the adjusted R-squared and the F-test. Then we need to say, all right, I remember Jim was telling us marginal costs and marginal benefits. So how do we detect things like heteroskedasticity, correlation, and multicollinearity? So heteroskedasticity, we do this brush-pagan chi-square test. The LOS doesn't ask us to actually do this, but it wants us to be aware of what this test can look like. And so typically we do p-values of 5% as well. And then we can correct them using White's corrected standard errors. And this is what I was saying to you earlier, is that lots of software packages will just say, hey, the BP test, you have conditional heteroskedasticity, and we're fixing it for you. If there is serial correlation, we're going to call it autocorrelation in time series, but you can call it either. I mean, either is appropriate here. You perform the DW test, and this is where you have to be careful, right? You got to go on this side, and have to go on this side for that range. And then there's the Hansen method to correct for those. Multicollinearity, this is a simple one. All you need to do is look at the T and F and R and see if they all agree with each other or if some of them disagree with each other, and then you can use that stepwise regression. And that takes us through all of these learning outcome statements. My advice is to link these with the simple linear regression so that you can learn both of those at both times. And then, most of the extra ones in this reading are on this page here, and then go through those extra learning outcome statements. And so remember, multiple linear regression is simple linear regression with just an extra variable or 2 or 3 or 10.